So in this problem, we're given a situation that looks like this. We have two sticks of uniform mass density, one of length 9 inches and one of length 12 inches, that are connected at right angles and are supported at their connection point such that the system will be in equilibrium. We know that the sticks form an angle phi with the vertical, as is shown, and we're asked to find what this angle phi has to be. So the important word to note in this problem statement is going to be, again, the word equilibrium. This is going to tell us that the sum of the torques on the system is going to be equal to 0, which is equivalent in this case to saying that the center of mass lies on the dotted line. Now this is not instantly intuitive for a lot of people, so I'm going to give a quick explanation for why this is the case. If the center of mass lies at the dotted line, we know that the torques, the torque on the system, or the torque due to gravity on the system, is going to be equivalent to just a single force that is applied at the center of mass. So then we'll have the torque due to gravity, which will lie along the center, which will lie along the dotted line pointing straight down, and we'll have the support force, which will also lie along the dotted line, but it'll be pointing straight up. Both of those will have torque equal to 0, and here's why. If we choose this point of connection as our reference point, then both the force of gravity and the support force will be pointing in the same direction as their distance vector from that reference point. Now if they're pointing in the same direction, then the sine of the angle between them is going to be equal to 0, which means that neither force will provide any torque, and thus the sum of the torques will have to be 0. So now all we have to do is we have to calculate the center of mass and make sure that it lies along this dotted line of angle phi. So now the center of mass, we're going to have to calculate the x-coordinate and the y-coordinate. The x-coordinate is going to be the mass of this piece, which is going to be 12 times lambda, that uniform mass density. We don't actually have to know what lambda is. I'm just going to put it in here so that my units will make sense, because 12 is going to be in units of inches. 12 lambda times 6 inches, since that's where the center of mass of this stick is, plus 0, because this is at the coordinate 0. I'm defining this to be the origin, divided by the total mass, which is 21 lambda. This gives us an x-coordinate of, canceling out a 3, we get 24 over 7 inches. Now, the y-coordinate we're going to calculate exactly the same way. We're going to have 9 lambda times 9 over 2, plus, again, it's going to be 0, and this is actually going to be negative 9 over 2. I'm sorry, because the coordinate is going to be in the negative direction, divided by 21 lambda. And now, again, we're going to cancel out a factor of 3, and we're going to end up getting 27 divided by 14 inches. So now these are going to be our x and y coordinates, and we just have to manufacture an angle phi that will put these coordinates upon that dotted line. So all we have to do is note that if the center of mass lies at some point along this dotted line, then this and this will form an opposite length and an adjacent length, such that the tangent of phi will have to be equal to this length divided by this length. So that will just be tan of phi is equal to YCM, the absolute value of YCM actually, because this is negative, divided by the absolute value of XCM. So this tells us tan phi is equal to 27 over 14, divided by 24 over 7. And canceling out the factors of 7, this just gives us 27 over 48, from which we can then cancel a factor of 3. We get 9 over 16, which tells us in the end the angle phi is equal to the arc tangent of 9 over 16. And so that's going to be our final answer.